Now remember that in statistical inference there are two broad categories of types of procedures or activities. One is hypothesis testing, which we just finished talking about, and the other is estimation. And within estimation we can talk about point estimation and interval estimation. So we'll start off talking about point estimation. So a point estimate is a single number that represents our best guess as to the true value of the population parameter being estimated. Now that point estimate, that guess, and when we say guess, it's a data-based guess, right? It's based on our data. It's hopefully close to, but we realize it's more than likely not going to be equal to the true population parameter that we're estimating. Hopefully it will be close to that parameter value, but we know that because a point estimate is a random variable, it's going to vary from one sample to the next, and so it's more than likely in any given situation not going to be exactly equal to that population parameter. On the other hand, an interval estimate is a range or interval of plausible values for the population parameter being estimated, along with a measure of the reliability of the estimation procedure. Now this measure of reliability is called the confidence coefficient or the confidence level, and it's expressed as a percentage. Right, so it might be 95%, 99%, 85%, whatever is appropriate for a given situation. Now, a confidence interval estimate is not as precise as a point estimate, but associated with this interval estimate, we have a high degree of confidence that the parameter being estimated is contained within the interval. So, again, if we go back to the previous slide for a second, a point estimate is a single number. Now, you can't get much more precise than a single value, right? I mean, that's very, very precise. But on the other hand, we know that that particular value is probably wrong. It's probably not exactly equal to the population parameter of interest. On the other hand, if we consider a range of plausible values, then that range it's not as precise as a single number, but we do have a much higher degree of confidence that the true value of the parameter is contained within that interval. So there's a trade-off between precision and confidence as it pertains to whether that estimate is accurate in terms of being equal to or containing that parameter of interest. Now the confidence coefficient, this measure of the reliability of the estimation, of the confidence interval estimation procedure, which is expressed as a percentage. It's also called the confidence level or the level of confidence for the interval. That is something that we choose. We choose the level of confidence that we want when we construct the confidence interval. Common confidence levels are 90%, 95%, and 99%. And we need to be careful how we interpret these. These percentages are not the probability that the confidence interval contains the parameter being estimated conditional on the data. They are a form of probability, but we need to be very, very careful how we go about interpreting this. So the confidence level, regardless of what it is, 90%, 95%, 99%, is not the conditional probability that the interval contains the parameter given the data. What it is an unconditional probability. So, and when we think about it as an unconditional probability, we have to kind of take a step back and look at the overall procedure itself. For a given interval, either the interval contains the parameter or not. From that context, the probability is either 0 or 1. 1 being it contains the parameter, 0 that it does not. But if we take a step back and look at the overall procedure, all right, and that is the proper way of interpreting a confidence level or confidence coefficient. It's a measure of the reliability of the procedure we're using, not the particular instance of that procedure in a particular case. Associated with a confidence interval, we're going to have the confidence limits. These are the endpoints of the confidence interval. And so we're going to have a lower confidence limit. That's the left or lower endpoint of the confidence interval. And we're going to have an upper confidence limit, which is the right or upper endpoint of the confidence interval. Now, I know that seems obvious, but I'm pointing this out because in some cases we're going to construct what we might call two-sided confidence intervals. And for those kinds of confidence intervals, both confidence limits, the lower confidence limit and the upper confidence limit, will be finite. But there are many situations where we want what is called a one-sided confidence interval. And so in that situation, when we construct a one-sided confidence interval, one of these confidence limits will be infinite. Either the lower confidence limit will be negative infinity and the upper confidence limit will be finite, or the lower confidence limit will be some finite value, and the upper confidence limit will be positive infinity. So we can have two-sided confidence intervals where both lower and upper confidence limits are finite. We can have a one-sided confidence interval where exactly one of the confidence limits is not finite. So it's either the lower confidence limit is negative infinity or the upper confidence limit is positive infinity. And the type of confidence interval that we choose will depend on the context and the nature of the problem that we're trying to solve. We'll see examples of all these. Now let's talk about confidence interval width versus the precision of a confidence interval. So confidence interval width and the precision of a confidence interval are inversely related in the sense that wider confidence intervals are less precise, they have less precision, and narrower confidence intervals are more precise. So for example, a confidence interval that goes from 50 to 100 is more precise than an interval that goes from 25 to, say, 125. The narrower the interval, the more precise the interval, the wider the interval, the less precise. Now, associated with many kinds of confidence intervals that we will construct, there is associated with it what's called a margin of error. Now, this shows up in those situations where we construct the confidence interval based on, let's say, a normal distribution or that kind of a scenario. So in this situation, what we do is we construct the confidence interval by starting off with a point estimate. All right, so a single value, that point estimate that we talked about just a minute ago, and then we compute the lower and upper confidence limits by going a certain distance to the left and to the right of this point estimate. Now that distance that we go to the left and to the right of the point estimate to get our confidence limits is called the margin of error. All right, so the margin of error is equal to 1/2 the width of the confidence interval for these kinds of intervals. Or another way to think about this is that the width of the confidence interval is 2 times the margin of error. Now the general form of what's called a 1 minus alpha times 100% confidence interval for a parameter, and this is based on those situations where the sampling distribution of the point estimate is normally distributed or approximately so, and in those cases the confidence interval is of the following form. Again, we start off with a point estimate and then we go a distance to the left and to the right equal to the margin of error. So the point estimate minus the margin of error gives us the lower confidence limit. The point estimate plus the margin of error gives us the upper confidence limit. And so now the natural question is, how do we calculate the margin of error? Well, for these kinds of intervals, and here this formula is based on the assumption that the sampling distribution of the point estimator is normally distributed, then the margin of error is equal to the product of what is called an interval coefficient, a z-value, okay, which I'm circling right here, and the standard error of the point estimate. So remember that the standard error is the standard deviation of the sampling distribution of that point estimator. And so the margin of error is equal to this z-value times the standard error of the point estimator. Now, what does this notation mean, this z-value or this interval coefficient? Well, in general, we define this quantity z sub p, so a lowercase z with a subscript p, to be such that the probability that the standard normal random variable is greater than z sub p is equal to p. So you see here that what is in the subscript of the z is over here on the right-hand side of this equality. All right, that's the corresponding probability. So let me show you a picture of what I'm talking about. I think it might help clear this up. So again, we're going to define z sub p. So here is a sketch of what I'm talking about. So the definition of z sub p. So z sub p is a value on the number line. Okay, and it's the number on the number line that if we think about the standard normal distribution, right? So this is the standard normal, centered at 0. In this picture, I'm assuming that p is less than 0.5. It doesn't have to be, but for this picture, that's why z sub p is to the right of 0. But anyway, so z sub p is the number on the number line such that the area under the curve to the right of that point is whatever's in the subscript. So p is in the subscript, and so That's what this area is right here. And so this what this implies then is, if I go back to the previous slide, the probability that the standard normal random variable is greater than z sub p is in fact p. Okay, now z sub p is called the upper pth percentile of the standard normal distribution. Now let's look at some examples. All right, so again, let me go back a few slides. Again, we use z sub p, all right, or a z value, okay, in constructing the margin of error. And notice that in this expression right here, and by the way, this is for obviously a two-sided confidence interval. Now notice that we've got alpha over 2 in the subscript of z. Where does that alpha represent? Well, alpha shows up right here in the confidence level of the confidence interval. So the confidence level of this confidence interval that we're constructing is 1 minus alpha times 100%. So it's part of this formula for the confidence level. Okay, so let's find the values of the interval coefficients for various confidence levels that we might use. For example, 90%, 95%, 99%. Okay, so we'll start off finding the interval coefficient associated with a 90% confidence interval. Okay, so if the confidence level is 90%, that means that 1 minus alpha times 100%, which is the definition of the confidence level, is equal to 90%. All right, let's divide both sides by 100%, so that means that 1 minus alpha is equal to 0.9. Now we solve for alpha. That means that alpha is equal to 0.1. Therefore, alpha over 2 is 0.05. And the reason we're doing this is we need z sub alpha over 2. And so what we need here for this 90% confidence interval, the interval coefficient is z sub 0.05. Now again, by definition, z sub 0.05 is the number on the number line such that the area under the curve, under the standard normal curve to the right of that point is what's in the subscript, which in this case is 0.05. And we can, from the standard normal table, conclude that z sub 0.05 is therefore 1.645. Now let's take a look at the portion of the standard normal table where we get this. And if you look at your standard normal table that you have available on Moodle, what we're going to do, we need to remember that the table we have is a right-tailed table, so it's giving us the probability, it's giving us these kind of right-tail probabilities. And we need the z value that gives us a right-tail area of 0.05. Now, if we scan through the probability columns, we'll eventually find this location, and we see that we don't see 0.05 exactly. We see 0.04947 and 0.05050. So 0.05 is between these two values. And so what we can conclude based on that is that the z value we need, z sub 0.05, is between 1.64 and 1.65. Now we could just, choose one of these two. In fact, what we might want to do is pick the value, okay, that is closest, that has the closest right tail probability to the desired area, which is 0.05. We see this one's just a little bit closer than this one, but I'm sorry, no, this one is a little bit closer than that one. But we also notice that 0.05 is almost exactly halfway between these two. And so because we're going to be using this z value a lot, we're going to be a little bit more precise in how we do it. And so we're basically going to do a linear interpolation between these two values to get the z value. And because this is about halfway between, because 0.05 is halfway between those, pretty close to that, we're going to choose the value halfway between 1.64 and 1.65. And so that is where we get the 1.645. Now for a confidence level of 95%, that implies then that alpha over 2 has got to be 0.025. And so the interval coefficient that we need is z sub 0.025. Now, by definition, that is the number on the number line that gives us a right tail area under the standard normal curve to the right of that point of what is in the subscript, 0.025. Now, if we go to the standard normal table, and scan down the probability column, we will find 0.025 exactly. And so that tells us that the z-value, z sub 0.025, is 1.96. And so that is where we get that. Okay, and then finally, for a 99% confidence interval, if the confidence level is 99%, we go through our calculations here. That means that alpha over 2 is 0.005. And so our z-value that we need, z sub 0.005, is the number on the number line that gives us a right tail area under the standard normal curve to the right of that point of what's in the subscript, 0.005. All right. Now I'm saying here that that's equal to 2.575. Let's go to the standard normal table and see if we agree with that. So if we go to the standard normal table and look in the probability columns for 0.005, we have a situation like we had, for the 90% interval. We don't find 0.005 exactly. We find 0.00494 and 0.00508. Now, and so we know then that z sub 0.005 is somewhere between 2.57 and 2.58. Now, because we're going to be using this fairly frequently in the context of confidence interval estimation, but also hypothesis testing, we're going to be a little more precise, and we're going to use essentially linear interpolation like we did before. All right, this 0.005 is almost halfway between those two numbers, and so we're going to use as an approximation to the z-value, the value that's halfway between 2.57 and 2.58, so 2.575. And so that is where we get that right there. And so to put all these results together, all right, the interval coefficients for 90, 95, and 99% confidence intervals. The interval coefficient for the 90% interval is 1.645. The interval coefficient for the 95% confidence interval is 1.96. And the interval coefficient for the 99% confidence interval is 2.575. Now, remember that the margin of error is equal to the product of the interval coefficient, the z-value, and the standard error of the point estimate. And so as the interval coefficient gets bigger, the margin of error increases as well. And so let's take that and think about the relationship between the confidence level of a confidence interval and the precision of that interval. So the confidence level and the precision of a confidence interval are inversely related. Increasing the confidence level, as we've seen, going back a few slides, if we increase the confidence level from 90 to 95% to 99%, what's happening to the magnitude of the interval coefficient? It's getting bigger, right? And so increasing the confidence level increases the interval coefficient, which therefore increases the margin of error. And it therefore increases the width of the interval, thereby decreasing the precision of the confidence interval. So increasing the confidence level decreases the precision of the confidence interval. On the other hand, if we decrease the confidence level, that's going to decrease the interval coefficient, thereby decreasing the margin of error, decreasing the width of the interval, and so increasing the precision of the interval.